Okay, so last couple of times actually, we've been talking about addition of angular momentum. And so we're going to do the general case today of addition of angular momentum. And so we have two angular momentum operators, J1 and J2. Okay, and then there are two different very good ways to form a complete set of commuting observables. One of them is J1 squared, J2 squared, J1z, and J2z. And that's called the product basis complete set of commuting observables. And then there's a different complete set of commuting observables we can make, which is J1 squared, J2 squared, and then the total J squared, and then the total Z component. And that's called the total angular momentum basis, or I'll just call it the total basis for short. Okay, and we can write the relationship between these representations as J1 product J2, that represents the product basis, is equal to the sum of representations, and I'm writing a circle with a plus through it for that. Okay, and it's the sum of all these different total angular momenta quantum numbers. Okay, so this is the total basis. Okay, so this thing I'm writing down is just telling you, it's just a reminder of what representations are involved. Okay, and so if we count the number of states in the product basis, we have states that are represented by just the J1z and J2z quantum numbers. And the total number of these basis states is equal to 2J1 plus 1. That's the number of different M1s you can have. And that's multiplied by 2J plus 1, 2J2 plus 1. That's the total number of M2s that you can have. And so then you can compare that to the total angular momentum basis states. And so if you count those, there's J1 plus J2. And then M can be any number from minus J1 plus J2 to plus J1 plus J2. So that has 2 times J1 plus J2 plus 1 states. And then there's J1 plus J2 minus 1, and all of its M values. And the number of those is 2 times the J for that, plus 1. That's the number of different M values. And then you keep going, and then finally you have absolute value of J1 minus J2 M. That has 2 times absolute value J1 minus J2 plus 1 states. And now I'm not going to do the combinatorics, but if you add up all of those things, you will find that you indeed get 2J1 plus 1 times 2J2 plus 1 states. So either way, that's the dimension of the Hilbert space. It's really easy to get that dimension of the Hilbert space in the product basis. You just multiply them together, and in the total angular momentum basis, you have to do them individually and then add them all up, but you get the same number in the end. Okay, so at last time we had noticed the fact that completeness usually tells you something interesting. And completeness says, in this case, that if I take a state Jm in the total basis, I can write that as this linear combination where I'm summing over all M1s, and I'm summing over all M2s of the product basis state M1, M2 times its bra times Jm. Okay, so all we've done there is we've written the identity operator here in a fancy way using completeness. That's the identity operator. And now it's a linear combination of product basis states, and the coefficients here are called Clebsch-Gordons. These are the Clebsch-Gordon coefficients for J1 and J2. So you can also write these, and depending on what book or source or table you look them up in, they might be written like this, where they explicitly tell you what the J1 and J2 are as part of the label of each state. Okay, but they're actually the same for both. That's why it's okay to leave them out. Okay, but those are your Clebsch-Gordon coefficients, and tables of these exist. You can just look them up. There's also software that will compute them for you, but you have to be a little bit careful because there can be different conventions. So almost everyone, in fact, I don't know a counterexample, almost everyone chooses these things to be real, but then some of them can be negative, and which ones you choose to be negative can be dependent on your conventions. Okay, so that defines the Clebsch-Gordon coefficients in terms of saying what are the total angular momentum basis states in terms of the product basis states. But now you can use completeness a different way. So completeness also says that if I take a given product basis state, again, we use a colon for a product basis sometimes if we are worried that it might be ambiguous, the notation might be ambiguous. So this we can write as a sum over all total angular momentum basis states. So I'm going to sum over all possible values of J, and the possible values of J go from absolute value of M1 minus M2 up to M1 plus M2. And then for each J, I'm going to sum over the possible values of its M from minus J up to J. And now I'm writing the identity operator in a fancy way. Okay, so again, this is the identity operator. It's just written differently now. And so now I've got the total angular momentum states, and I've got these coefficients right there. And the key thing to notice is that these are almost the same coefficients. In fact, if you stare at this, you'll realize that's the complex conjugate of this. And so these are the complex conjugates of the Clebsch-Gordon coefficients. Except it gets even better than that because it's actually always possible to choose the Clebsch-Gordon coefficients to be real. And therefore, the complex conjugate, if you do choose that convention, which is a really smart idea, then the complex conjugate makes no difference at all. And so these literally are the same coefficients. Okay, so that's because we can and will choose them real. And by the way, it's a non-trivial fact that this is consistent with the choice that we've already made for the YLMs. So that's another convention. And when we chose that convention, we were actually looking ahead a little bit. The place where this comes into play is if the J1 and J2 are both integers. Okay, so everything works. You choose your YLMs according to the convention we chose, and then the Clebsch-Gordon coefficients are going to be real. Okay, and so what we've got is we've got a 2-for-1 deal. We can write total states, we can write total states in terms of product states with the Clebsch-Gordons, and we can write product states in terms of the total states with the same Clebsch-Gordon coefficients. All right, questions on that so far? All right, so let's review what we found in Clebsch-Gordon coefficient language. So we have found so far, first I'll write the states that we found. So we found for the case of spin 1/2, product spin 1/2, we found that gave total spin 1 and total spin 0. And so if we write in the total basis in this column, there was a state 1, 1, which in the product basis was up arrow, but I'm just going to rewrite that today as 1/2 colon 1/2. So that's the same thing as up arrow, up arrow. And then we had 1 minus 1, which was in the product basis minus 1/2, minus 1/2. That's also known as down arrow, down arrow. And then there was 1, 0, which was 1 over the square root of 2, 1/2 colon minus 1/2, plus minus 1/2, 1/2. And then we had 0, 0 in the product basis was this orthogonal linear combination. With a minus sign. Okay, and so now from that table of equalities, we can just pick off the non-zero Clebsch-Gordon coefficients. So any Clebsch-Gordon coefficient that I'm not about to mention is just 0. Okay, and so let me write them the way they would be possibly written in a table. So first you just write the J1 and J2. Then I write the M1 and M2. And then in the other part here, I again rewrite J1 and J2, even though it's redundant. And I write 1, 1. And we read off here that that's equal to 1. That's just read directly from here. Okay, and then we do the others. So there's, I won't write the 1/2, 1/2 over and over again. Here I'll just write 1/2 minus 1/2 and 1, 0. That's equal to 1 over square root of 2. So is this one minus 1/2 plus 1/2, 1, 0. Okay, and these things generally will involve lots of square roots of rational numbers. You never get something like pi or anything weird like that. Okay, so this one's also 1 over square root of 2. And then you have minus 1/2, 1/2 in the product basis with 0, 0 in the total basis. This is minus 1 over square root of 2. And then finally, the last non-zero one is if these are both minus 1/2, and this one is 1 and minus 1, then that's equal to 1. Okay, so all of these once you've worked out the relationship between the total basis and the product basis, every term in here is a Clebsch-Gordon coefficient, and then you can make a big table of what they all are. Okay, so that was one example we did. And then another example we did is a typical situation where you have an orbital quantum number and a spin, for example, for the electron. And so according to our general rule, this is L plus a half plus L minus 1/2 in the total basis. And in fact, we worked out what these were. So I'll write here in the total basis, and here's a column for the product basis. And we found that L plus 1/2 m is equal to square root of L minus m plus 1/2 over 2L plus 1 times, in the product basis, m plus 1/2 minus 1/2. And then there's another contribution, which is square root of L plus m plus 1/2 over 2L plus 1, m minus 1/2, 1/2. And we got this by using the J minus operator. Okay, and then by orthogonality, we got this in also. So it's just slightly different square roots. But the same two states are involved for a given m. There's the minus sign there, L minus m plus 1/2 over 2L plus 1, m minus 1/2, 1/2. So when I wrote this, I was saying L could be an orbital angular momentum, but of course it could also be a spin. Nothing goes wrong with this derivation if I say L is actually equal to 1/2. And if L does equal to 1/2, then these things that I've written here, you can check, are just the same things that I've written here. They're really the same thing if L equals 1/2. But now I can plug in any L, including an integer, to work these things out. Okay, so now we can just write down what are the non-zero Clebsch-Gordon coefficients. They're in one-to-one correspondence with the non-zero terms in these linear combinations. These are for L cross 1/2. So first there's m plus 1/2. That should be a colon. Minus 1/2. L plus 1/2 m. We just read that off as this square root of L minus m plus 1/2 over 2L plus 1. Okay, and then m plus 1/2 colon minus 1/2 L minus 1/2 m is a different square root where we just basically flip the sign of m. And there are various rules for how you can get some Clebsch-Gordon coefficients from others by doing things like flipping the sign of m. In the last lecture on Friday, I'll tell you some of those rules that govern these things. Okay, but then there's, continuing on, there's m minus 1/2, 1/2, L plus 1/2 m. That matrix element, Clebsch-Gordon, is L plus m plus 1/2 over 2L plus 1. That one happens to be the same as, as this one. Those two happen to be equal. And then there's this one. Finally, m minus 1/2 1/2 L minus 1/2 M is equal to minus sign times the first one. Okay, so these happen to be related by a minus sign. Okay, so now that we got the Clebsch-Gordon coefficients and we got them by writing the total states in terms of the product states, now we can reverse them using the completeness relation that I wrote down earlier without doing any extra work to get the product basis states as linear combinations of the total basis states, which is sort of the reverse operation of what we did. So, for example, M plus 1/2 colon minus 1/2 is equal to this Clebsch-Gordon plus this one. Okay, but this isn't usually the best way to write it because we're starting with a state that we supposedly know here. And so we know this number M plus 1/2, and so let's rename M to make this thing be something simple. Okay, so what we're going to do is we're going to rewrite with the definition that M sub L is equal to M plus 1/2. Right, so the idea there is that what we really want is we're given a product basis state with known M1 and M2 quantum numbers, namely their M sub L and the spin, in this case, the down spin. And so what I should do is now just use this relation everywhere on the right-hand side to be consistent. And so this turns out to be square root of L minus M sub L plus 1 over 2L plus 1. Okay, and I'm rewriting M as M sub L minus 1/2. And then the last term is L plus M sub L over 2L plus 1, L minus 1/2, M sub L minus 1/2. Okay, so what we've done is we've used the Clebsch-Gordon coefficients, but we've just rewritten them in a constructive way so that we get any product state as a linear combination of the total angular momentum basis states that contribute. So notice we can tell which ones contribute because we know the first angular momentum z component and the second angular momentum z component add up to ml minus 1/2. And so that means the only things that can appear on the right-hand side are states that have that same value of ml minus 1/2, but they can have different values of the total angular momentum. And the two different values they can have are L plus 1/2 and L minus 1/2. So without doing anything else, you would have known that it was a linear combination of these two states. And then what we've done using the Clebsch-Gordons is to find out what the coefficients actually are. Okay, and then you can do the same thing for the other combination. So similarly, and I won't go through the details as much, but skipping to the end, M sub L plus 1/2, you can write as square root of L plus M sub L plus 1, it turns out, over 2L plus 1. There's always a square root of 2L plus 1 in the denominator. L plus 1/2 m sub l plus 1/2 minus sign square root of L minus m sub L over 2L plus 1. Okay, so that's the linear combination. And so once again, if you look at the thing you're starting with here, you know that the total z angular momentum quantum number is going to be ml plus 1/2. So it has to be a linear combination of the two possible states that you can make that have that. And then the total angular momentum can be different for those states. And so you get a general linear combination, and the Clebsch-Gordon coefficients tell you what the coefficients are. Okay, so just as a note again that all Clebsch-Gordons are real in our convention, but they're not all positive. And so that's what different sensible conventions do, is they choose which ones you're going to make negative because you can't make them all positive. And so in this convention, that's the one that happens to be negative. Okay, questions on that? All right, so now let's finally explain how you do the general case. And for the general case, I can't write down a simple formula for the coefficients like we did, for example, here. But what we can do is give an algorithm so that you can teach your computer to compute these things. Or you could do it on your own, I guess, for specific values of J1 and J2. Okay, so the general case where you have J1 and J2, and we're going to assume that J1 is greater than or equal to J2. If it's not, then that just means you chose them wrong and you should reverse them. Okay, and then we're going to start with the highest state, which means the highest Jm state. That means you choose J as big as it can possibly be, and you choose M as big as it can possibly be, and those are both the same number. Namely, they are J1 plus J2. So if your two spins are lined up along the z direction, both of them as lined up as they can be, then that's the number that you'll get for M. And since that's the largest number you can get for M, it's also the largest number you can get for J. Okay, and there's a unique state with that property. So we call that state in the total basis J1 plus J2, J1 plus J2. But it's also equal in the product basis to J1 colon J2. The individual M's are both as large as they can be. That's a unique state. There's only one of them with that property that has the maximum possible J sub z. Okay, so because it's unique, we don't have anything to do. That's our first relation between the total states and the base and the product states. And now to find more things, we're going to do what we did before, which is to act with J minus, which is J1 minus plus J2 minus. And so the idea is first we act with this version of it, then we act with this version of it, and then we set them equal and find out what we get from that. Okay, so as the first step, we take J minus acting on the left-hand side of the boxed equation. And we remember what J minus does. It was H bar times a square root. And when we plug in what goes in the square root, it's J1 plus J2 plus J1 plus J2 multiplied by J1 plus J2 minus J1 minus J2 plus 1. Okay, and then the state that we get out has the second argument lowered by 1. So it's J1 plus J2 minus 1. Okay, and then inside the square root, some nice things happen. One is this part just cancels. I didn't mean to do that. It cancels like this. Okay, and so this whole thing is h bar square root of 2 times J1 plus J2. Okay, and we've lowered the m value by 1 unit. Okay, so that's this version of acting with J minus. Okay, and it's also equal to this version of acting with J minus. So also equals J1 minus plus J2 minus. And now we write this version of the state that we started with in the product basis. Okay, and so now we have to do those individually. So there's an h bar times, again, a square root, which in this case is going to be J1 plus J1 times J1 plus J1 minus 1. J1 minus 1, J2. So we've lowered the M1 value by 1. And then the second term looks very similar, except J1 and J2 are interchanged everywhere. So J2 plus J2, J2 plus J2 minus 1 times J1. And now we lower M2 by 1 unit. Okay, and now J1 plus J1 plus, this should have been plus 1 here. And this should have been plus 1 because, and this should have been minus. Oops, made a few mistakes here. Okay. So this should have been minus. And this one should have been minus. And that's because then this turns into just 1. And this turns into just 1. Okay, and so this is equal to h bar square root of 2 times J1 plus h bar square root of 2 times J2 times this state. Okay, and now what we are doing is we're setting this equal to this. Oops, one more little thing I did wrong here. This should have been a colon because this is in the product basis. This is also in the product basis. Okay, and so now setting those things equal to each other, we learn that the total basis state J1 plus J2, J1 plus J2 minus 1 is equal to, the h bars of course cancel, and we have 1 over square root of J1 plus J2. The square root of 2's also cancel, and we get square root of J1, and we get square root of J2 here for this one. Okay, and so we had previously derived this exact same thing with J1 equals J2 equals 1/2. And then we did it with J1 equals L and J2 equals 1/2. Okay, so it's the same idea. And then we're going to do what we did before, which is to keep acting with J minus until we can't do it anymore. So keep acting with J minus. And then here's what you eventually must get to. You'll find that J1 plus J2 minus J1 plus J2, that total angular momentum state has to equal minus J1 minus J2. Okay, and the reason it has to equal that is that's the unique state that has the lowest possible value of J sub z. You get it when you line up the two angular momenta to be as much as possible in the negative z direction. And so that's why there's only one of them. And so this is an opportunity for a check. Because it could go wrong, right? If you drop a minus sign or a square root of 2 or something like that somewhere, then when you get down here, you won't get this relationship. And then that's kind of bad news. Actually, I should have put a J2 here. Oops. If you don't get this relationship, it means you made a mistake somewhere and you have to go back and trace it. That's bad news because it might mean more work, but it's good news because now you can at least find the mistake. Okay, and so now once we've done this, we've got all the states that have J, the total angular quantum number, equal to the sum of J1 plus J2. All right, but that's not all the states. There's more. So now we need to work on, and notice I haven't written down what they all are. I wrote down the first one, and then I wrote down this one, and then I told you what you have to get on the end, but I haven't told you what the intermediate ones are. Those can be kind of a mess. Okay, but now we need to work on states with J equals J1 plus J2 minus 1, which is the next lower combination. And to do that, what we're going to do is we're going to start with the maximum M, just like we did before. But now the maximum M that you can have is not J1 plus J2, it's going to be J1 plus J2 minus 1. Okay, so what we do is we write down the state that we're trying to get. This is the state with the maximum M. And what we know about it is it's a linear combination now of two possible states. So I'm going to write A times J1, J2 minus 1 plus B, J1 minus 1, J2. Those are the only two states that can have this value of M here. And so it must be some linear combination. And a good news that we know is that it's not degenerate. This state isn't. The reason we know that is because J1 squared, J2 squared, J squared, and J sub z are a complete set of commuting observables. And the first C in complete set of commuting observables is saying that all redundancies or all degeneracies have been eliminated. And so by definition, there can only be one solution for A and B up to some multiplicative constant. Okay, so now how are we going to find out what A and B are? We're going to use the following facts. The first is that this state has to be orthogonal to this state, which we had already found up above. Okay, so it's orthogonal to that. we're also going to require that it has norm 1, which just means that magnitude of a squared plus magnitude of b squared has to equal 1. And then that's not enough to quite finish determining a and b. The last thing we need is the Condon-Shortley convention. So this is just arbitrary, it's just a convention. But we agree to choose A to be positive. And so we choose A to be positive, assuming again, as we've already mentioned, that J1 is greater than or equal to J2. That's the Condon-Shortley convention. And now if you put all these facts together, okay, that uniquely determines A and B for you. Okay, and in fact, I could actually write that out for you, but we're not going to be able to write the general relation for all these coefficients anyway. So I will skip doing that solution directly. Instead, this is just all about the strategy. So the strategy is, now that we've got this state, we're going to just start acting with J minus again. So we apply the operator J minus, and that's going to get all of the other states that are of the form J1 plus J2 minus 1 with any possible value of m. Here we just did the largest one, but now we start acting with J minus on that, we're going to get all the lower m's, okay, until we get down to the last one, the one that has J, so the last one is going to have m equals minus J1 plus J2 minus 1. Okay, and so that's done with all of the states that have J1 plus J2 minus 1. And now we need to go to the states that have one lower value. So states with J equals J1 plus J2 minus 2. Okay, and just like we did before, we're going to start with the maximum value of m. So we start with max m, which in this case is going to be J1 plus J2 minus 2. And so let's write down what that state could possibly be. Okay, and now if you think of what are all the possible states that could have that value of m, there are 3 of them. So I'm going to write a linear combination of 3 possible states in the product basis, which are J1, J1 colon J2 minus 2, or I could have J1 minus 1 colon J2 minus 1, or I could have J1 and J2 minus 2. Okay, I can't have one with J, sorry, that's wrong. So it's J1 minus 2 and J2. So I can't have one that has, for example, J1 minus 3, because then J2, the m value for the second spin would have to be J2 plus 1, and there are no spins, there are no states with that value of J2, because the largest it can be is J2. Okay, and so that's the most general linear combination you can have. And so now it looks like we're in trouble because we have 3 things to solve for. How are we going to solve for A, B, and C? So it turns out it is possible to do. And you can even solve for them uniquely. And so here's the things that you need. Again, we're going to use orthogonality. So this state that we've written has to be orthogonal to two different states now, namely J1 plus J2, J1 plus J2 minus 2, and J1 plus J2 minus 1, J1 plus J2 minus 2. Okay, so we know it's orthogonal to those because these are eigenstates of observables with different eigenvalues. Here are the different eigenvalues. In this case, it was total angular momentum J1 plus J2 minus 2. And here it was J1 plus J2. And here it was J1 plus J2 minus 1. So those have different eigenvalues for the total angular momentum squared, and therefore they must be orthogonal. So we get to use that fact. Okay, the second fact we're going to use is we get to require that this thing have norm 1, which just says that magnitude A squared plus magnitude B squared plus magnitude C squared has to equal 1. And because this involves only the magnitudes, you can't quite solve for all three of A, B, and C. You can only solve for them up to a phase. And so once again, you appeal to the Condon-Shortley convention, which just says you choose A to be real and positive. Okay, and so those conditions put together will allow you to solve for A, B, and C uniquely. Okay, and so now you act with J minus again until you can't anymore, until you get 0. And then you use orthonormality again. Okay, and you keep alternating using J minus and orthonormality. And eventually you get to the state or states that have total angular momentum J1 minus J2 in magnitude with different values of M. And then once you've finished with those, then you're done. Okay, so here's the sort of map of the general scheme of how this works. Okay, is you start, let me make a column here for J equals J1 plus J2. And you start with the unique state, which is J1 plus J2, J1 plus J2. You act with J minus. That just lowers the M value. You act with J minus again. It lowers the M value again, one more. Okay, you keep acting with J minus over and over again. You get to J1 plus J2 minus J1 minus J2 plus 1. You act with J minus one more time, and you get J1 plus J2 minus J1 minus J2. That's where you can do a nice check to make sure it's the right answer. Okay, and so you're done with that column. And now you use orthonormality, specifically orthonormal to this state. And that gives you J1 plus J2 minus 1, J1 plus J2 minus 1. Now you act with J minus, and you get another column of these things with different values of M. And you keep doing that. Keep acting with J minus until you get this state. J1 plus J2 minus 1, minus J1 minus J2 plus 1. Okay, and as a check, at every stage, you can compare these different states to make sure they're orthonormal. Okay, so that one has to be orthonormal to that. But those are checks. You don't actually need them in order to do anything. Okay, and then here you again use orthonormal. Okay, and you get this state here, J1 plus J2 minus 2, J1 plus J2 minus 2. You act with J minus again. You get some state here. Whatever state you got here, you use orthonormality. Okay, and so that's the general scheme of how you can compute the Clebsch-Gordon coefficients. All right, so you can do that, or you can look them up in tables, or you can use this algorithm to compute them by a computer, which is also a good option. Okay, so next time I'll tell you some of the general rules that Clebsch-Gordon coefficients satisfy that may not be necessarily completely obvious from this algorithm, but are nevertheless true. And then we'll discuss a little bit of applications of this to atomic physics. All right, any questions about this?
I have a general question, Professor.
Okay.
So, among the homework assignments and the midterms, would we have the option of requesting you to eliminate the lowest grade?
I think not, because yeah, we didn't have that in the original rules. So I think we'll just go with the grading scheme as it is.
I have a question from the notes.
Okay.
Okay. On page, hold on.
Maybe I'll turn off the recording here.
Yeah. Thank